So the previous chapter, chapter 7, we learned about energy conservation. And the core idea, the thing that's most important to take away from that chapter is the idea that energy is conserved. Now, what we mean by conservation of energy is that energy isn't created or destroyed. And the way that worked out in the previous chapter was that if you've got an object that's an isolated system where all the forces acting on that object were conserved or were conservative forces, then what would happen is that object would start with a certain amount of mechanical energy. Mechanical energy being your kinetic energy plus your potential energy. And whatever amount of energy that object started with, as it moved around and maybe sped up or slowed down, the total energy of the object would remain constant. So, for instance, if you have a roller coaster that starts off on a high hill, it's going to have a bunch of potential energy at the top of that hill, but very little kinetic energy. However, as it slides down the hill, as long as there's no frictional losses, what's going to happen is as it goes down the hill, the potential energy would drop, but the kinetic energy would go up by the same amount, so that the total of those two energies never changed, right? And we were exploiting that fact to solve all kinds of problems. Now, if you had a situation where uh, you're yeah, gross, where you had a non-conservative forces, the total mechanical energy wouldn't be conserved. Now, that doesn't mean that the energy just vanishes or disappears. But what it does mean is that if I have an object that, say, slides across the ground uh, and friction does work on it, it's taking energy away from that object, but the energy is not destroyed. It just turns into something like heat. And if you were to account the kinetic plus the potential plus the heat, that total amount of energy would also still not be changing. And so that's the idea of energy conservation or a conservation law. So physics is full of conservation laws, laws in which some quantity that we're talking about remains the same through some process. And oftentimes, problems that are difficult to solve from one perspective can be made much, much simpler if we exploit the fact that there are conservation laws in play. So what's going to happen in chapter 8 is we're going to introduce a second conservation law that we can use to solve problems. And the concept that's going to be conserved is a concept called momentum. Now, momentum is one of those words that you might have heard in casual conversation outside of a physics context. Usually when I hear somebody who's not a physicist use the word momentum, it's during football season when I'm watching a ball game. And, you know, I grew up in Texas, so I'm required by law to be a Cowboys fan. It has to happen. I don't want to be, but there's no way around it. And so inevitably what happens is every year, Dak Prescott throws an interception and the color commentator in the game will say something like, well, that interception sure does shift the momentum of the game. Or scoring that touchdown before halftime sure does mean they have a lot of momentum going into the second half. And when he says that, inevitably what he means is that one of those two teams, the team who has all the momentum, they're just rolling right over the other team. They are impossible to stop. And that's kind of a good way to think about what momentum is in the context of physics as well. You can think of momentum as being a measure of how difficult an object is to stop. That's kind of what it's going to end up being. So what would make an object hard to stop? Well, if it was traveling really fast, right? Things going really fast, it's hard to stop them. So clearly, momentum is going to depend on the velocity of an object. Now, what else would make an object hard to stop? Well, if an object has a really big mass, it takes a lot of force to make it accelerate. So having a big mass will also translate to having a lot of momentum. So when we define this term momentum, that's where we're starting from. We're literally going to say that it's going to be the mass of the object times the velocity of the object. And this quantity is what we're going to call momentum. Now, for reasons that I don't even know, when we define momentum, the letter that we're going to use for momentum is P. Why P? I don't know. I didn't make it up. So when you see P, you're going to think momentum. And momentum is literally going to be defined as the product of an object's mass times that object's velocity. Piece of cake. Now, one thing I should point out, velocity is a vector. It has both a magnitude and a direction. Mass is a scalar. It's just a number. And if you multiply a scalar times a vector, you get another vector that's stretched out or compressed, but it's still in the same direction. So that means that momentum is also going to be a vector. And that means we're going to have to treat it like a vector. We're going to have to do things like add or subtract it like vectors. The direction is going to matter. It's going to be important. So I just want to call that out because it will make some things more complicated here in a little bit. So just remember, momentum is a vector. The direction matters. Now, a few years back, my wife is really big on the every anniversary there's like some kind of stupid theme, like the first year is like the paper anniversary, the next year is like the cotton anniversary, the 50th anniversary is like the diamond anniversary. I don't know, there's like some list, and I'm pretty sure it's just a conspiracy by Hallmark to make people buy stuff. But every year for our anniversary she gets me a gift that is themed to whatever the theme is for that year's anniversary. And so one year it was the paper anniversary. And so my anniversary gift from her that year was a book. And the book that she got me was a copy of Isaac Newton's Principia Mathematica. Now, that's the book where Isaac Newton originally proposed his three laws of motion. And when I got the book, I was super excited because I'm thinking, man, I'm a physicist in the 21st century. I know more physics than Isaac Newton ever knew. So even though he was a brilliant guy, I should be able to understand this book super, super easily. But when I went to read the book, what I found was that it was unintelligible to me. And I'm like, how can that be? He's describing physics that I literally teach every year to undergraduates. This should be like second nature to me, but reading the book was really difficult. And part of it was because the way that we teach Newton's laws, or even the way I think about Newton's laws, is different from the way that he originally envisioned it. We've sort of changed the way we approach the problem since then. And as a consequence, he was using terminology that was unfamiliar. He was using techniques that were unfamiliar. It was very, very different. And one of the easier ways that it was different was that when Isaac Newton originally wrote the three laws of motion, he didn't write them the way we learn them in most physics textbooks. Instead, he wrote them all in terms of momentum. And when you do that, it changes the way each of those laws would read. So hopefully at this point, you guys know the three laws of motion. If you don't, you're in trouble because you should know them by now. The first law of motion is called the law of inertia. And the way we learned it back in chapter 4 was that an object tends to remain in motion with a constant velocity unless acted upon by a net force. Now, if I wanted to rephrase that the way Isaac Newton phrased it originally, I wouldn't talk about velocities. I wouldn't say an object tends to remain in motion with constant velocity. Instead, I would rewrite it to say an object tends to remain in motion and all I'd have to do is replace the word velocity with momentum. As acted on by a net force. Now, making that one little one-word change in the first law of motion doesn't really affect very much. I don't get any special insight out of it. I don't know. It doesn't really help us very much. But that's how Newton originally phrased it. Basically, momentums don't like to change. If you've got a momentum that's to the right, your momentum wants to continue being to the right. And in order to make your momentum be something different, you have to push on it and exert some kind of net force. So, whatever. This is not super helpful. Now, the second law of motion, way more helpful. Now, how do we learn the second law of motion? F equals ma. Again, this is the thing that at your 20-year college reunion, if you show up and you cannot tell me what Newton's second law is, I swear to God, we're taking your degree away, right? If you learn nothing else this semester, you're going to know that F equals m freaking a. But again, he never wrote F equals ma in his book. Instead, he wrote this in terms of momentum. Now, how's that supposed to look? Well, in order to make sense of that, remember that acceleration is defined as the rate of change of velocity. And so if I take Newton's law the way we learned it, replace the A with delta V over delta T, now we're getting closer to how Newton envisioned it. But wait a second, I have m times delta V, and m times V is momentum, so therefore m times delta V should be the change in momentum. So that's actually how Isaac Newton originally wrote the second law of motion. He said that the force was equal to the rate of change of your momentum. If there's a net force acting on you forward, your forward momentum will increase. If there's a net force acting on you backwards, your forward momentum will decrease. Right? That's what Newton's second law looks like, the way Newton originally envisioned it. Now, occasionally what will happen is we'll rearrange this. We'll multiply both sides by delta t. And we'll write it like this. So again, we just rearranged it. And what this says is that if you have an object under the influence of some net force, if you take how hard you push it with times how long you push it for, that's going to tell you how much the momentum has changed by. So the harder you push, the more your momentum changes. The longer you push for, the more your momentum changes, right? This is just Newton's second law kind of rewritten a little bit. But when we write it like this way, we give it a name. We call it the impulse momentum theorem. And the reason we call it that is because it tells us how much my momentum has changed by. And this product right here, the force times the time, is called impulse. So we would say that, if you push something with 2 newtons of force for 5 seconds, you will have delivered an impulse of 10 Newton seconds. Okay, whatever. So the impulse momentum theorem is, maybe sort of useful. It's certainly a different way of looking at F equals ma, so it's not worthless, but still not that groundbreaking. The real action is going to happen when we think about the third law. Now, what was the third law the way we learned it? Well, we learned that for every force on an object, if I push an object forward, it's pushing me with the exact same force, but in the opposite direction. Every force has an equal but opposite force acting on the pusher. Now, here's the implication of that. Here's how the third law is going to play out. Because remember, the third law implies that forces always occur in pairs. If I push you, you're pushing back against me. There's an action and a reaction force. Now, what's going to happen is, if I've got two objects in an isolated system, object one and object two, and let's imagine that these two objects aren't interacting with anybody else. The only two forces we're going to have to deal with is object one pushing object two and object two pushing object one. Now, when those two things interact in some way, the third law says the force that one of them feels is going to be the same as the force the other one feels, just one's positive, the other's negative. The other thing I know is true is that the time that those two forces are pushing for are going to have to be the same. I can't push you for 3 seconds and you only push me back for 2 seconds. That's nuts, right? As long as I'm pushing you, you're pushing me. So the time for those two objects is going to have to be the same. But that has an implication, because if the two forces are the same, but with opposite signs, and the two times have to be the same, that means the amount that the momentum of the two objects will change also has to be the same. If one of them has a momentum go up by positive 10, the other object's going to have to go down by negative 10. So the total change in momentum for both objects together has to be 0. And that's the implication of the third law. For an isolated system, the total momentum of all objects in the system is constant. That's awesome. This tells me that momentum, this m times v quantity, is a conserved quantity. And as long as I have objects that are interacting only amongst themselves, the total momentum of that system has to remain conserved. Now, what do I mean by an isolated system? Well, it's a system that only interacts with members of that system. So here's kind of an example of what I mean by that. All right, imagine I got 10 people in a room, and everybody in that room had $50 in their pocket, right? So if there's 10 people and each person has $50, that's a total of $500 that people have in the room. So think of the money in the room as being like the momentum. Now, if I have an isolated system, what I mean by that is that the interactions are only going to be between people in the room. So let's say that the people in the room start buying and selling stuff from one another. So maybe I've got $50 and I give you my $50. Well, now I have no money, but you have $100. And what's going to happen is, if all the buying and selling occurs among the 10 people in the room, yeah, some of the people may end up with more money, but other people are going to end up with less money than they started with. The total money for everybody is still going to be $500 no matter what. No amount of buying and selling within that room is going to change how much money exists in that room. And that's what we mean by an isolated system in terms of momentum. If I have a bunch of balls bouncing around each other, as long as they're only bouncing off one another, the total momentum of all the balls will stay the same. Now, for a non-isolated system, maybe what happens is one of the 10 people in the room orders a pizza, right? So the pizza guy shows up and the person gives $20 to the pizza guy. The pizza guy leaves. Well, now what's going to happen is that $20 that person just spent didn't go to one of the other 10 people in the room. And so the total amount of money in the room has now gone down by $20. There's only $480 in the room where there used to be $500, right? That's because a member of the room interacted with somebody outside the room. Now, in physics, we can always just redefine what the system is that we're talking about. Because what's going to happen, imagine the pizza guy didn't have any money before. If you now redefined what I'm talking about for the system as being the 10 people in the room plus the pizza guy, well, now what's going to happen is you had $500 before, the pizza guy takes the $20 and leaves, that's still $500, right? So as long as you define your system widely enough, momentum will always be conserved. But you've got to make sure when you're doing a problem that if you've got objects interacting with one another, you have to count the momentum of all the objects. Otherwise, it might appear that some of your momentum is going to go missing because maybe the pizza guy runs off with some of that money and you're not going to see that anymore. So you have to count the pizza guy in part of your system if you're going to give the right answers. But this is cool. It means momentum is a conserved quantity, and it means that I can use momentum to solve problems that might otherwise be intractable. So what's that going to look like? Well, frequently what's going to happen is momentum conservation is going to end up being helpful in situations where two objects collide. Now, why is it helpful there? Well, think about the impulse momentum theorem for a second, right? The change in momentum is related to F times T. But think about like something like a car crash. If two cars crash into each other, the forces from one car to the other car, they tend to be enormous. F tends to be super, super huge. However, car crashes happen very, very fast. The amount of time over which they are elapsing is often measured in fractions of a second. And so it's often difficult to get good measurements of what the forces are over such short time scales. So finding F or finding T are both very, very difficult if I'm dealing with like two things colliding, because the collision tends to happen and it's over in a few milliseconds. However, the momentum change before and after is much, much easier to assess. So we can avoid not having good information about this by only thinking about the problem in terms of this. It's going to make problems where things crash into each other way, way easier than they otherwise would have been. So that's going to be our plan. So anytime I have an isolated system, I can say that the sum of all the momentum of all the objects initially has to be the same as the sum of all the momentum of the objects at the end. The momentum before is going to have to equal the momentum after. Now, bear in mind, this is not just one momentum, it's the momentum of everybody. And this is the momentum of everybody after. So this could end up being a whole bunch of terms. Also bear in mind that I'm adding up a bunch of momentas, but momentum is a vector. So when I add them together, I have to add them in a manner consistent with vectors. So this is a super simple thing to write down, but implementing this might be complicated depending on what our scenario looks like. Let's solve a problem with this. Now, I want to solve an easy problem. So I'm going to solve a one-dimensional momentum problem. So in this problem, all the motion is going to be along a single straight line. It's all going to have X components, but no Y components. And that'll make my life way easier because I won't have to deal with breaking things into components with vectors and SOHCAHTOA and all that stuff. It'll be easy. So here's the scenario. All right, imagine I've got an ice skater. And I'm choosing an ice skater because I want the ice skater to not exert any forces on her surroundings. And again, I always seem to assume it's her. That's sexist. So his surroundings. This person, their surroundings. There we go. This person is going to interact with their surroundings. But because they're on a bunch of ice, there's no friction. And because there's no friction, I don't have to worry about them interacting with the planet Earth. I don't have to keep track of the momentum of the planet Earth. I can just keep track of their momentum. So let's give this person a mass of, let's say, 60 kilograms. That's not ridiculous for a human. And I'm going to call that object 1. So the skater is object 1. And right now they're just on this ice skating rink, sitting around minding their own business, not moving. So right now they have a velocity of 0. So that's v1 initial is 0. Now what's going to happen is somebody off camera here is going to throw a snowball at the head of this poor defenseless skater. So this jerk throws a snowball, and I'm going to call that object 2. Now, this is a ridiculously huge snowball. This is the mother of all snowballs. It's got a mass of a whopping 1 kilogram. That's a 2.2 pound snowball flying right at this poor person's head. And let's have it booking it pretty fast. Let's have it be traveling with a speed of 20 meters per second, right at this poor skater's head. Now, what's going to happen when that snowball hits the skater? Well, let's assume, for the sake of this problem, that what happens is that snowball slams into the side of this poor person's head, and when it does so, it's going to exert a force on them, right? The snowball is going to exert a force, and it's going to push the skater to the right. And because the skater is not under the influence of any friction, that force to the right is going to cause the skater to accelerate to the right. So they may have started out at rest, but they're going to end up moving to the right. Now, whatever force the snowball puts on the skater is going to put the same force on the snowball. So the snowball will accelerate to the left, meaning it will slow down. And let's assume, for simplicity's sake, that this big, wet, sticky snowball splats onto the side of the person's head and just sticks there. So now I've got a skater who's clearly moving to the right with a big, nasty snowball stuck to the side of their head. And what I would like to do is determine with what speed will the skater be traveling after the collision occurs. I want to figure that final velocity out. Now, what I don't know is what force the snowball exerts on them. I have no information about that. I also don't know about the time over which that collision occurs. The snowball is going to splat and stick in a very short amount of time, and I have no information about what that time is. However, even though I can't do anything with that, I can think about this problem in terms of the momentum in the problem. And the way I can do that is by requiring that momentum in this problem be conserved. So before the collision, my total momentum is going to be the momentum of the skater. Well, that's just going to be the mass of the skater times the starting velocity of the skater, plus the momentum of the snowball. That's the mass of the snowball times v2 initial, the starting velocity of the snowball. And that's got to equal, on the other side, the final momentum. Well, after the collision, the object 1, the skater, is moving with some speed and some final velocity. Meanwhile, the snowball is stuck to her head. Again, sexism, darn it. V final. But because it's stuck to the person's head, the velocity of the snowball has to be the same as the velocity of the skater. They're both going to have the same speed. So I don't have to call it V1 final and V2 final for this problem because they're both going to be the same. So the momentum before equals the momentum after, and conveniently, the momentum of the skater before was 0. So this goes away. So all I'm solving is M2 V2 initial equals M1 plus M2 V final. Since these are both times the same thing, I can just factor the M2 out. And if I want to know what speed they end up with, I just got to get this by itself. So I'll have M2 times V2 initial divided by M1 plus M2 is equal to V final. And this is 1 times 20 divided by 60 plus 1. So 20 over 61 is a little bit less than 1/3. So, without knowing any information about the forces that were being exerted or the time over which that collision occurs, I was able to figure out that afterward, that skater is going to be traveling in the positive direction, so to the right, yay, at a speed of 0.327. So from momentum conservation, I was able to solve that problem. Let's make it more complicated. Let's imagine that the skater is not caught unawares by this unprovoked snowball attack. And instead, the snowball is going to come in, and rather than let it splat against the side of their head, they just reach out and catch the snowball. Now, if you reach out and catch that snowball, the time the catch occurs over might actually be longer than the time that it splats against your head with. So the forces and the times, those all might be different. But in terms of the momentum is still going to have to be conserved. And my initial state is still going to be the same as it was before. My final state is still going to have the skater and the snowball moving together because they're going to be holding the snowball after they catch it. So if I was solving for the speed that this person's going to have after they catch the snowball, well, I still got the same starting momentum, same ending momentum, same velocity, same answer. So whether it splats them in the head or they catch it in their hands, it's not going to matter. They're still going to be flying to the right at that speed. Well, that was fun. Now, let's ramp it up again. Now that the skater has got this snowball in their hands and they see the person off screen over here who they were attacked by, their natural inclination is going to be to throw that snowball back at the jerk and hopefully clock them in the head. So I want the skater to throw the snowball back towards the person who originally threw the snowball at them with the exact same starting speed that the snowball originally had. So now what's going to happen is we're going to have a different final state. Now the snowball is going to be traveling to the left at 20 meters per second. But after the person throws the snowball back, what's going to happen to the person? Well, while they were throwing, they were already traveling to the right at a speed of 0.327. And what's going to happen is, as they're throwing the snowball to the right, they're exerting a force on the snowball to the right. The snowball, according to the third law of motion, is exerting a force on the person, to the left, to the right. If they're exerting a force on the snowball to the left, the snowball is exerting a force on them to the right, which means they're going to accelerate in that direction, which means they're not going to stop. They're already traveling in that direction at a speed of 0.327, and they're going to end up speeding up. And they're going to end up traveling, presumably, to the right at an even larger speed than 0.327. So when I go to solve this problem, I'm going to use momentum conservation. My initial momentum is the same as it was originally. This guy here traveling to the right at a speed of 20. This person not traveling at all. So I've got M2 times V2 initial, because before the catch, this person wasn't moving. After the collision, both the snowball and the person are both going to have momentum. So I'll have the person M1 times V1 final, and I don't know what V1 final is, plus M2 times V2 final. That's the momentum of the snowball after it gets thrown back. And so if I want to know what speed the person has after they throw the snowball back, I'll solve for V1 final. So I'm going to get this to the other side by subtracting. So I'm going to have M2 V2 initial minus M2 V2 final equals M1 V1 final. And therefore, when I divide by M1, all I've got to do is plug in my numbers. Now, M1 was the mass of the skater, which we said was 60. Mass 2 was the mass of the snowball, which was 1 kilogram. V2 initial is 20 meters per second. And a very common mistake is students will look at this problem and say, oh, what is V2 final? What's the velocity of the snowball after the collision? They'll look up here and say, oh, look, that's 20. Yay! And they'll plug 20 in here. But then look what's going to happen. If they make that mistake, they're going to have 1 times 20 minus 1 times 20. That's 0. That would suggest that the person throws the snowball and stops dead. And we know that doesn't make sense. We know that while they're throwing the snowball, they're pushing the snowball one direction. The snowball's pushing them that direction. They're going to accelerate in that direction. So I know going in that the final speed of the person is going to have to end up being larger than 0.327. So if I'm getting a different answer than that, I'm making a mistake. Now, what is the mistake? Velocity is a vector. So this is 20 meters per second to the left. Before, that was 20 meters per second to the right. So if this to the right is the positive direction, this was positive 20, this is to the left, I got to slap a minus sign on it and call it negative 20. So now it's going to be minus negative 20, which is plus 20. That's 40. 40 over 60 is a 0.667. And notice that fits with our expectation that after throwing the snowball, the person who's the skater is going to end up traveling even faster than they were after they caught the snowball. But still, we were able to solve that entire problem, and not once did I have to worry about how much force got exerted. I didn't need to know, as long as I could break the problem down in terms of the momentum before and the momentum after. And that's super powerful. We can solve a lot of really complicated, nasty problems if all we ever have to deal with is the momentum. Now, this is one of the easiest ways we can do this because all the things were along a single line. It can get more complicated than that. Plus, there are some other complications that we could throw out as well. To make sense of that, I should have gone upstairs and got my dreidel. One of my things that doomed me as a child to becoming a physicist was at my grandmother's house. She had a Newton's cradle on her coffee table, and you probably have seen one of these before. I have one that I keep in the class for this lecture, and I think I have one upstairs, but I forgot to bring it down, and I'm too lazy to go upstairs now. So what they are is like a little set of balls. And what happens is these 5 identical balls hang by strings, and if you lift one of them up and you let them go, what invariably happens is most of the balls remain stationary, but on the other side, exactly one ball will pop up, right? And that always blew my mind as a kid, because you could do really weird stuff. Stop. Is there a reset button? Oh, that's cool. So let's just reload the page. So darn it. This is not the sim I wanted, because I can't do the thing I want to show. God bless. So what used to blow my mind as a kid is if I have one ball, I get one ball popping up on the other side. But what I used to do as a child was I would have not just one ball, but two balls go up. If I pull two balls up and I let this thing go, a weird thing happens. Two balls pop up on the other side, right? That was wild. I was like, what's going on there? If I started it over and had, three balls pop up, I'd get three balls pop up on the other side. And even as a child, I was like, man, how does it know? How does this inanimate object know what to do? You could get really crazy. And you could lift one ball up on either side. And when you let those guys come down, you got that sort of effect. Or my favorite was this one. There have two balls on one side and one ball on the other side. And what would happen is they'd switch every single time. This is way more impressive when you have the honest to God real thing. But this is what would happen. And I would do these little experiments with my grandmother's Newton's cradle on the coffee table. And it blew my mind. And my parents couldn't explain how this worked. So I ultimately had to go to college and take physics classes in order to understand what's going on here. It was pretty weird. Now, at this point, we know enough physics that we can explain most of what's happening in that instance. Because if you think about it, obviously we're doing this during the momentum chapter, so that momentum is going to be part of the answer. And certainly what's going to happen is if I've got, let's say, 5 balls, and one of these balls comes down with a certain speed, let's say it's got a speed of 5 meters per second, and they all have a mass of 1 kilogram, then if the first 4 of those balls stop dead and the last ball pops up with a speed of 5 meters per second, obviously the momentum here and the momentum here are the same, right? It's going to be this m times that v before and the same m times the same v after. So clearly in that situation, momentum is conserved. So obviously momentum conservation is part of the explanation of this. But unfortunately, it's not the only explanation, or it's not the full explanation. Because what if I had a situation where I had one ball come in with a speed of 5, but instead of having exactly one ball pop up, what if all 5 balls move simultaneously, but they all had a speed of only 1 meter per second? Well, that's going to be the same momentum. Right here, the momentum is 1 times 5. And here, since all 5 balls are moving, it's going to be 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 1. That's still 5, right? I have 5 momentum if I add up all the momentum for everybody here that I had there. So momentum would be conserved, and yet this is not what happens. This is what happens. What if instead of having one ball pop up on the other side, what if I had 3 of them stop dead and 2 of them pop up? However, these 2 each had a speed of 2.5 meters per second. Well, now what's going to happen is the momentum that I have after is still going to be 1 times 2.5 plus 1 times 2.5. That's still a total of 5 units of momentum. which is what I started with, and yet this is not what happens. Only this. So momentum conservation is only part of the story. The reason these situations don't ever happen, and this one does, is because in addition to conserving momentum, we also have to think about the energy before and after. So one way to think about that is, in this original example, how much kinetic energy do I have? Well, these guys are all at rest. They have no kinetic energy. This guy, however, my K initial, would have a kinetic energy of 1/2 times m times v squared, right? That's kinetic energy. And since v is 5 and m is 1, well, 5 squared is 25 times 1 is still 25 times 1/2 is 12.5 joules of kinetic energy before that collision occurs. Now, if one ball pops up on the other side, I still have 12.5 joules of kinetic energy. None of my kinetic energy went missing if one ball pops up on the other side. But how much kinetic energy would I have if I had this situation? Well, for that situation, that'd be 1/2 times the total mass is 5 kilograms. The total velocity is 1 meter per second squared. Oh. So what's going to happen is, if all 5 balls were to pop up traveling 1/5 of the speed, I would still have the same momentum before and after, but I'd have way less energy, right? I started with 12.5 joules. I finished 2.5 joules. 10 joules just suddenly vanished somehow. What if I had done this situation? How much kinetic energy would I have had then? Well, here I would have had 1/2 times 2 times 2.5 squared. So 2.5 times 2.5 is 6.25. 6.25 times, well, heck, 1/2 times 2 is going to cancel. Notice I have more energy left than I had here, but still way less than I started with. So what's going to happen is, in these collisions with the Newton's cradle, the reason that we get the behavior that we get is because not only am I conserving momentum, I am also conserving kinetic energy. I have the same energy before that I have after. In each of these other possible cases that could work, the kinetic energy is different before and after. And just to be like super thorough, there's other possibilities we didn't even consider. What would happen if this guy comes in at a speed of 5, and after the collision, he bounces backwards at a speed of 2.5, 3 of them stop dead, and 1 of them bounces forward at a speed of 2.5, right? This would also conserve, 7.5. This would also conserve momentum, right? Because the mass, so m times 2.5 is 2.5, but it's to the left, so it's negative. So it's negative 2.5. 1 times 7.5 is 7.5, and 7.5 minus 2.5 is 5, which is what I started with. So that's other situations that could conserve momentum, but again, the energetics will be weird. Jasmine, you had a question.
Yes, so at the top one, where is that a 2 times 2.5?
Which one here?
Over the where the 1/2 the equation is. Yeah, is that 2 times 2.5 squared, or
over here? Yeah.
Yes.
Because here I'm doing the kinetic energy, and I have 2 of them moving, so the mass was 2, right?
Okay.
But the speed was half as big.
Oh, okay. That's why I was wondering where the 2 came from. I didn't catch that. But okay.
Yeah. Just like over here when I did this one, I had all 5 moving, so I had a mass of 5.
Got you. Okay.
Ball, I said, had a mass of 1.
Okay. Thank you.
So, yeah. So, what's happening in this situation is, for these collisions, momentum and energy are both being conserved. Now, here's what's going to happen. these things are possible, but they don't happen with the Newton's cradle because of the kinds of collisions that we end up having. Now, if any of you guys ever watched Mythbusters, back when it was on the air, I used to love that show. There was an episode of Mythbusters where they got to thinking about these little Newton's cradle desktop toys, and one of the things that they observed was, you always see these things like on like coffee table size racks, right? The balls are usually maybe about that big. And in Mythbusters, they used to love to always make things ridiculous. Like if they're going to explode something, they're going to explode the heck out of it, right? They always kind of ramp things up to the biggest level possible. And so they got to wondering, like, what would happen if they built a Newton's cradle where the balls weren't just these little tiny things, but were instead like giant wrecking balls, the kinds of things you use to knock down houses? Would they still work? And so they tried it. They got 5 big cranes and they put 5 one-ton wrecking balls from each of those cranes. They pulled one of them back and had it hit the others. And when it did, this is not what happened. You didn't have one ball pop up on the other side with exactly the same speed. Instead, what happened is that one ball came in and swung, hit the others, and all 5 of them moved simultaneously. So in that situation, they started with a bunch of kinetic energy. The momentum was still conserved, but you ended up with a lot of energy going missing. So depending on the nature of your collision, the energy may or may not be conserved. There's plenty of situations where it's not. And it's just that the particular situation that we see with a desktop toy is one where it is. So we're going to take collisions and we're going to divide them into 2 broad categories, depending on how the energy sorts itself out. The first category is what we call an elastic collision. In an elastic collision, momentum and energy are both conserved. Think about like the word elastic. You think about like elastic waistbands, like on your underwear, or like elastic rubber balls. They're things that are bouncy. You stretch them out and they snap back to their original shape. So in an elastic collision, you start with a certain amount of energy, they bounce, but then they snap back, and all the energy you started with, you're going to get it right back. In an elastic collision, all the forces of the 2 objects banging into each other end up being conservative forces, so that none of the energy is vanished. But if you have non-conservative forces that are acting during that collision, then you may have an inelastic collision. Now, inelastic collisions, they're going to still conserve momentum because momentum is going to always be conserved. So momentum is conserved, but energy is not. So in these little examples we were doing, having one guy pop up on the other side, that was an elastic collision. But this case and this case were both inelastic collisions. We started with 12.5 joules and we ended up with something less. But notice, when it comes to elastic collisions, I only have one possibility, starting with 12.5 joules and ending with 12.5 joules. But with an inelastic collision, there's lots of possibilities. I could have started with 12.5 and ended up with 2.5 or 6.25. Both of these are inelastic, but that's a whole lot of range. That's different possibilities. So for inelastic collisions, there's a spectrum of possibilities. You don't necessarily have to lose all the momentum, but you're going to lose some of it. And there's a special case of inelastic collision known as the perfectly inelastic collision. So in a perfectly inelastic collision, what's going to happen is you're going to lose the maximum amount of energy possible. So momentum will be conserved, but you're going to lose as much energy as possible. Now, note when I say the maximum amount possible, I don't necessarily mean 100% of the energy, but it's the most energy you can lose while still conserving the momentum. Because even in these, momentum is going to be conserved because, and I cannot stress this enough, momentum is always conserved.
It's a law.
Thank you, sweetheart. So these collisions here and these collisions here, you may not necessarily know them when you see them. It's not going to be immediately apparent to you that you have an elastic or an inelastic collision. So if I'm trying to determine whether a collision is inelastic or elastic, I will frequently have to use momentum conservation to solve the problem. Thank you, sweetie. To solve the problem. And once I've solved the problem, then I'll look to see, do I have more energy at the beginning than I have at the end? Or do I have the same energy at the beginning and the end? If the former, then that suggests it was inelastic. And if the latter, that suggests it was elastic. So for that, you'll just do the math the same way we did over here. We use momentum to solve the problem and figure out what final velocity I had to have. And then we look to see whether the energy was the same before and after. Because they were different, it was inelastic. Had they been the same, it would have been elastic. Perfectly inelastic collisions, though, you're going to know them when you see them, right? And the way you're going to know them when you see them is that anytime you have a perfectly inelastic collision, the objects will stick together. So if you see two things hit and stick together and move together after the collision, you know going right in that it's going to be a perfectly inelastic collision. And what that means is that any other possible outcome would end up having more energy than that outcome. And you can kind of see that in the example here we did before. If this guy comes in and hits these guys, and afterward all five of them move together, this is an example of a perfectly inelastic collision. And notice in that example, we started with 12.5 joules of energy, but we only finished with 2.5 joules of energy. So a vast majority, but not quite all of our kinetic energy vanished. It turned into heat and deformation and sound, stuff like that. Now, in this other situation, which was also inelastic, but they didn't all stick together because these guys moved separately from these guys, we ended up with more energy left over. So we still lost some energy, but we did not lose as much as we did when they all stuck together. And that will, in general, be true. Notice the very first example we did, the ball stuck to the person. This was a perfectly inelastic collision, and energy was therefore not going to be conserved. How much energy did we have in this problem before the collision? Well, before the collision, we had 1/2 times the mass of the snowball, which was 1, times the velocity of the snowball, which was 20, squared. 20 squared is 400 times 1/2. We started with a whopping 200 joules worth of kinetic energy in that snowball. But afterward, both the person and the snowball were moving. So the ending energy is going to be 1/2 times, well, the mass is going to be 60 plus 1, so 61. And the speed was only 0.327. And when you crunch those numbers, I can't do that one in my head. I get only 3.12 joules. So we started with almost 200 joules, and we ended up with barely anything, right? Now, where did all that energy go? Well, that snowball, when it splats into the person's head, it squishes up and changes shape, and it's not going to bounce back to its original shape. So you had to exert a force through a distance to squish that snowball. You're not getting that back. You also will end up causing the molecules of the snowball to heat up a little bit. That snowball is going to get a little wet and gooey from the raising temperature. So the energy still exists. It just no longer is in the form of mechanical energy. It's turned into something else. So those are your easiest, straightforward, one-dimensional momentum conservation problems. How are we doing?
I get.
Dr. Fleming, can I see the page with the elastic collision one more time, please?
Yeah. So
I'm gonna take a screenshot of it so I can write it down. You can proceed.
okay, you can take a screenshot off the video after I post it.
Oh, okay. Thank you.
Yeah. So I've lost track of where that page went. All right. So here's what we're going to do. I want to play around with elastic collisions specifically for a second. Because if I have a collision that I don't know whether it's elastic or not, I can always use momentum conservation to solve it. So for instance, imagine I've got two objects. Here's object one, here's object two. And I'm going to have these two guys bounce into each other. They're going to have some kind of collision. Now, object one is going to have some mass, m1. It's some number. We'll worry about it later. Mass two is going to have some other mass, m2. Again, I'll worry about the numbers later. We're going to do this as generically as possible. And before the collision, object one is going to have some v2 initial. V1 initial, stupid. All right. Object two is going to have some v2 initial. So before the collision, each of them may have some velocity. Now, maybe one of the velocities is 0. Maybe object one is traveling to the right and object two is traveling to the left, and they bang into each other head on. Maybe object two is traveling to the right, but it's going really slow. And object one is traveling even faster to the right, so it comes up and it has like a rear end collision. Maybe that's what happens. Doesn't matter. All that matters is before the collision, they both have some velocity and they both have some mass. And so that means that the total momentum of both objects before the collision is going to be the mass of object one times his starting velocity plus the mass of object two times its starting velocity. Now, after the collision, they're going to bounce. Maybe they bounce apart and he goes this way and he goes that way. Maybe they stick together and they both travel the same direction. Doesn't matter either. After the collision, he's going to have some amount of momentum. It'll be his mass times whatever final velocity it's got. He's going to have some momentum. It'll be his mass times his final velocity. So if momentum is conserved in a one-dimensional collision between these two objects, that equation is going to be the way I've implemented the generic P initial equals P final. If I wanted to throw some third object in the mix, all I'd have to do is add a M3 V3 initial and an M3 V3 final to either side of this equation, right? I can build the equation using this idea for whatever situation I've got. Now, what's going to happen is if I wanted to say, tell you the starting speeds and have you predict the final velocities after the collision, well, right now you wouldn't be able to do it because right now I have one equation, right? And if I told you both the M's and I told you both the V initials, you still wouldn't know V1 final and you still wouldn't know V2 final. So you'd have two unknowns and wouldn't have enough information to solve the problem. Now, if I told you one of the final velocities, however, you could for sure figure out the other final velocity. So for instance, if I told you that mass 2 was 2, or mass 1 was 2, mass 2 is 3, V1 initial is 5 meters per second to the right. V2 initial is 3 meters per second to the left. So he's going to go like that. He's going to go like that. And then I told you that after the collision, V1 final has to travel to the left with a speed of 3 meters per second. All right. If I tell you that, the only thing you wouldn't know would be V2 final, which means with this piece of information, you could solve that problem. All you'd have to do is get V2 final by itself by subtracting that off. So I'd have M1, V1 initial plus M2, V2 initial minus M1, V1 final equals M2, V2 final. Then I divide both sides by M2. So V2 final would equal all of this. And then I can just plug my numbers in. So M1 was 2 times 5 plus 3 times -3 minus, what was M1? It was 2 times V1 final, which is -3. So 10 minus 9 plus 6. Jesus, that was the easiest question we've ever asked in this class. This is super easy. We could do this in our sleep. But in order for you to answer the question, I had to tell you what are the final velocities. However, what if I change the game a little bit? What if instead of telling you just the starting velocities and one final velocity, what if I told you something different? What if I told you all the starting velocities, and I also told you that you knew going in that the collision was going to be elastic? That gives us another arrow in our quiver. So let's try that. Same scenario.
Oh, wait, Dr. Chibi, I'm sorry, not Dr. Chibi, sorry. Dr. Fleming, can you bring that back real quick? I can take a screenshot of it.
Yes, ma'am.
Thank you.
You're welcome. All right. So same scenario, except this time I'm not going to tell you one of the final velocities. However, I'm telling you that it's going to have a one-dimensional elastic collision. Now, because I know momentum is conserved, I can still say that M1 times V1 initial plus M2 times V2 initial has to be the same as M1 V1 final plus M2 V2 final. That's the same thing we had a minute ago. That's still got to be true. That's momentum conservation. However, if I know going in it's elastic, that means the total kinetic energy before and after also has to be the same. That's going to allow me to write a second equation. I'll be able to say that his kinetic energy before, which will be 1/2 times M1 times V1 initial squared, plus this guy's kinetic energy, 1/2 times his mass times his velocity before the collision squared, has to equal his momentum, or excuse me, his energy after, plus his energy after. So again, all I'm saying is the energy before is the same as the energy after. That statement, however, is an equation. But now what's going to happen is I have two equations and two unknowns. I don't know V1 final or V2 final, but each of them appears in both equations. And we know from algebra that if I have two equations and two unknowns, that is a solvable problem. So all we've got to do is eat this onion ring and then solve it. So I apologize, that onion ring was calling to me. So I'm going to do this math. And here's what's going to happen. I'm going to do this math as generically as I can. I don't want to plug any numbers in until the last minute because I want to get a result that's going to be true no matter what my numbers are. And what's going to happen is the algebra on this is going to get a little intense. So what I would strongly recommend you do is to not focus so much on the specifics of the algebra, because we're going to do this one time and have a result that we're going to not have to derive again. But instead, pay attention to the concept. What's the concept? We started by saying we have the same momentum before as after and the same energy before as after, and we're going to algebraically combine these two equations. That's the big idea. The algebraic manipulations that we're going to do, I'm going to do pretty quickly, and they're going to be pretty intense. So bear with me. Usually what I tell my students during class is if you're taking notes, what I would not do is write down everything I write down, but instead write down everything I say while I'm writing it down, because that's way more important. So here's what we're going to do. I'm going to manipulate each of these equations just to get them in a better form. Let's take this equation over here. And what I'm going to do is I'm going to get all the object 1 information on one side of the equal sign and all the object 2 information on the other side. So here I have 1s and 2s. Let's take the 2s and move them over here. And let's take the 1s and move them over here. So this equation is going to turn into M1 V1 initial minus M1 V1 final equals, and over on the other side, I'm going to have what was there before, M2 V2 final minus this thing, M2 V2 initial. So I just put all the 1s on this side, all the 2s on this side. Then I said, oh, this has M1 in common. Let's factor all that out. So I've got M1 times V1 initial minus V1 final. Over here, I'll do the same trick. I'll factor the M2s out. So this is just this momentum conservation equation kind of rewritten a little bit. Now, what about this energy conservation equation? I haven't used this one yet. Well, the first thing I notice is every single one of these terms has a 1/2 in it. If I just multiply everything by 2, all those 1/2s are going to cancel. Cancel, 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 cancel. The second thing I notice is that, again, I have object 1 and object 2 stuff on each side. Let's do the same trick here that we did here. Let's get all the 1 stuff on one side and all the 2 stuff on the other side. So this guy, I'll have M1 V1 initial squared minus M1 V1 final squared equals M2 V2 final squared minus M2 V2 initial squared. I just moved this to that side, so that's why it's negative. Oh, but wait a second. Let's factor the heck out of this. Notice there's M1s in both of these. I can factor out that M1. And what's more, it's going to leave behind V1 initial squared minus V1 final squared. And from back in the day when you guys learned algebra, one of the things you guys learned was that if I have a squared minus b squared, right? And you wanted to factor that, that's the same as a plus b times a minus b, right? Because if you FOIL this out, what's going to happen is you'll have a times a squared, b times negative b is going to be negative b squared. And then you'll have the cross terms. You'll have b times a, so that's plus ba. Then you'll have a times negative b, that's minus ba, and these things cancel, right? So this is one of those tricks you learned back in algebra class a million zillion years ago. I can use that here, and I can factor this as being V1 initial minus V1 final times V1 initial plus V1 final. On the right-hand side, I'm going to do the same trick. Factor out the M2s. I'm going to have V2 final minus V2 initial times V2 final plus V2 initial. Now, here's why that's cool. The thing I notice is that my momentum conservation equation, I end up with this expression. For my energy conservation equation, I end up with this expression, but I notice that, oh, look, this right here appears there. This right here appears there. So I notice that these two equations have something really, really in common. And I'm going to have to algebraically combine these two equations anyway. And normally what I would do is I'd take one of my unknowns and I'd get that unknown by itself and I'd plug that into the other equation so that unknown goes away. But here, if I just take this equation and divide it by that equation, so on the left-hand side, I'll divide by this. And on the right-hand side, I'll divide by this. This big, ugly, nasty expression has a lot of stuff cancel. And I end up with this equals this. That is awesome. So now what's going to happen is I've got V1 initial plus V1 final equals V2 initial plus V2 final. That is excellent. Now, how can I use this to my advantage? Remember, what is my goal? I want to find my final velocities. I'm trying to find this or this. And this is a pretty simple expression. Let's get V2 final by itself. Let's just solve for V2 final. I'll get that V2 final is going to equal V1 initial plus V1 final minus V2 initial. I just rearranged it to get V2 final by itself. Now, if I take this expression for V2 final and I go back to one of my original equations and replace V2 final will no longer appear. So let's go back to my original equation, which is this one right here. I'm going to replace V2 final with all this stuff. So now this equation has turned into M1 V1 initial plus M2 V2 initial equals M1 V1 final. Now it's got to be plus M2 times all this. So we plus M2 times that plus, I got to distribute the M2, so M2 times that plus, but that's got a minus sign, so minus M2 times that. And it looks kind of ugly, except now the only thing in this equation that I don't know is V1 final. Now it appears twice, so I'll have to combine some like terms, but I can get V1 final by itself super easily. So let's keep all the V1 final stuff over here, and let's get everything that's not V1 final to the other side of the equal sign. So here I've got a V1 initial. Here's a V1 initial. Let's get these two terms combined. I'm going to subtract this from both sides. So I'm going to have M1 minus M2 times whatever V1 initial is. I just combine this term and this term. Now, what about this? I have M2 V2 initial, and on the other side, I have negative M2 V2 initial. I have to add this to both sides to move it over, so I'm going to end up with two of these. So it'll be plus 2 M2 V2 initial. Now that's got to equal, now over here I have M1 times V1 final and M2 times V1 final. If I factor out the V1 finals, that's M1 plus M2 times V1 final. So now to get V1 final by itself, all I got to do is divide everything by this. So I'm going to have this M1 minus M2 over M1 plus M2 times V1 initial. And then I got to take this and divide by that. So 2m2 over m1 plus m2. I like to group these terms together because it's mass over mass. So this is really just a dimensionless constant. And boom, this right here is going to give me V1 final anytime I have a one-dimensional elastic collision. Because if I started from this and this, these will always simplify to this. So I don't have to do all this gory algebra every time. I know that once I see the situation, I can jump straight to here. So this is one of those few cases where I advise memorizing an equation, or at least having that equation handy. Now, the good news is we now know what V1 final is. The bad news is we got to do this now again for V2 final. However, I'm lazy and pretty quick on the draw. And one thing I realize is that if I just renamed the two balls and I called U2 and U1, I'd have to get the same equation, right? Which means if I just swap all the numbers, the equation should still work. Which means V2 final should be the same equation, but with all the numbers swapped. So instead of being M1 minus M2, it'll be M2 minus M1. And instead of being V1 initial right there, it'll be V2 initial. Over here, instead of being 2M2, it'll be 2M1. And instead of being V2 initial here, it'll be V1 initial. So that's my solution for V2 final. And again, it's going to be true anytime I've got a one-dimensional elastic collision. Now, let's go back, way, way back, to the very first problem that we started with. Right? We started with that Newton's cradle, right? And the thing about that Newton's cradle was that all the masses were exactly the same. So if I have two balls with the same mass and they collide and they have a one-dimensional elastic collision, well, these two equations we just found are going to have to work, right? And if M1 is the same as M2, what's going to happen? Well, if I go to these equations, let's do it this way. If M1 is the same as M2, then M1 minus M2 is going to be 0. 0 over anything is 0. 0 times V1 initial is 0. So this whole first term is going to die. Over here, I'm going to have 2 times the mass over, and if these are both the same, that's going to be 2 times the mass as well. This divided by this is going to turn into 1. So it'll turn into 0 V1 initial plus 1 V1 final equals, or V2 initial equals V1 final. In other words, V2 initial equals V1 final. Do you guys follow that?
A little bit.
Yeah. I'm just saying if M1 and M2 are the same, this right here is 0. That clears that thing out. But if these two things are the same, 2M2 and M1 plus M2 is going to be the same number. So that turns into 1. So I'll have V1 final equals 1 V2 initial plus 0. Now, for V2 final, the same trick. V2 final is going to equal, well, down here, this is going to be 0. This would be 1 equals V1 initial. But wait a second. What does that mean? If this is object 1 and that's object 2 started out at rest, right? It started out with a velocity of 0. So V2 initial is 0. That means that V1 final is going to be 0. When this guy comes down and hits, he's going to stop dead. Meanwhile, V2 final is going to equal V1 initial. It's going to go flying away at the exact same speed that that guy had originally. So this implies that if the masses are the same, they swap velocities. Now, for the Newton's cradle, what's going to happen is you have 5 of these collisions in a row. But each time the first ball comes in, it hits the second ball, it stops, the other one goes shooting off at the same speed. He hits the next guy in line and they swap. Then he hits the next guy in line and they swap. And they keep swapping all the way down until eventually you end up with one ball popping up at the same speed as the original one. So part of why that little desktop toy works the way it works is because they're elastic collisions and all the masses are the same. Notice if the masses are different, you will get a different result. Imagine that instead, object 1 comes in with a velocity of 3 meters per second. And object 2 over here comes at it with a speed of -3 meters per second, is V2 initial. However, if the masses were the same, then what would happen is they would swap. He would go bouncing to the left at a speed of 3. He would go bouncing to the right at a speed of 3. However, if their masses are different, if mass 1 is equal to, let's say, 2 kilograms, but mass 2 is equal to something like 4 kilograms, then what's going to happen is they will not swap. If I go for V1 final, that's going to equal M1 minus M2 over M1 plus M2 times V1 initial plus 2 M1 over M1 plus M2 times V2 initial. And when I go to calculate that, that's going to be 2 minus 4, so -2 over 2 plus 4, 6. So -2 over 6 is -1/3 V1 initial. V1 initial was 3, plus 2 times M1, that's 4 over 6, so 2/3, times V2 initial, which was -3. So what's going to happen is I'm going to have -1/3 times 3 is -1. -2/3 times -3 is -2.
Could you move the page down just a little bit?
Oh, I'm sorry. It's just a picture.
Thank you.
Yeah. So that's going to be the V1 final. So V1 is going to hit and it's going to bounce back in that direction. But what's going to happen to V2? Well, for that, it would be M2 minus M1 over M1 plus M2 times V2 initial plus 2 times M1 over M1 plus M2 times V1 initial. And when I go to evaluate that, what's going to happen is it'll be 4 minus 2 is +2 over 6. That's going to be 2/3 times V2 initial. V2 initial is going to be -3. Meanwhile, over here, it's going to be plus 2 times M1. Well, that's 2 times 2 is 4 over 6. So 2/3 of V1 initial, which was +3. So 2/3 times -3 is going to be -2. 2/3 of +3 is going to be +2. It's going to stop dead. So you see how that works, right? And all we're going to have to do is utilize that relationship anytime we have a one-dimensional elastic collision. Now, here's where I have to caution you, because on, your final exam or the next exam you have with momentum on it, I guarantee you there'll be a problem where there's a collision. You're going to have to solve some stuff. And what's going to happen is when it comes to this equation only works if you've got, for sure, a one-dimensional elastic collision. In order to use that equation, you have to know going in that the collision is one-dimensional and elastic. And I guarantee you, I don't know who it is, but somebody does it every semester. Somebody's going to take a collision where you don't know that it's elastic, or heck, where you know, in fact, it's not elastic, or whether it's not one-dimensional, and you know that as well. And they're going to try to use those equations anyway. And if you use those equations for a collision that you do not know going in is elastic, I'm going to give you a giant red X and 0 points, right? Only use that if you know for a fact, if the problem tells you it is elastic. Because if it's not elastic, it's going to give you the wrong answer. All right. So we're out of time for today. What's going to happen tomorrow is we will figure out what to do if I have a collision that involves motion that's not restricted along a single straight line. How do I deal with momentum conservation in a situation where the motion is two-dimensional? And as you might expect, it's more complicated. Any last-minute questions before I hit the button?
No, no, thank you.
All right, guys, then have a good day. I will see you tomorrow.